when we have at the destination, okay, the checker creates a new checksum from the combination of the message, and if the new checksum is all zero, then the message is accepted lah. Okay, so here in this mechanism, we have these different types of bits, okay, where you can have the bits that you want to have, okay, and then you have a generator where you can have another additional m bits to the number of m bits that you have to send. Okay, so say that you have 1 until 10 bits message, okay, m bits message. So you have to add another m bits because you can add all these different bits, okay, all together, and you can create this message checksum. Okay, and at the receiver part is where you can use these m bits to check either there's any error from the whole message that you already sent. Okay, so if it's all zero, then you can accept it, but else perhaps you need to drop it. Okay, so basically is that they use an additional to do this. Okay, so and then I can show you the step later on. Okay, but basically you can add all these few numbers, and then you need to do what we call one's complement, right? And you send the packet, okay, plus the checksum. Okay, so and then with respect to that, okay, so if you receive at this checksum, if it's summed correctly, it will give us a total sum of zero checksum lah. So this with respect to the simplest way of doing error checking is by having this also lah. Okay, so just now you can see that it is based on decimal number. The one that actually being used is using this what they call it hex binary number. Okay, so say that if we have this, all right. So say that here we have a few bits that you want to send. This is the first m bits. This is the first. This is the second m bits. Okay, you sum it up. Okay, basically you sum 0, 1, 1 is 0. Okay, 1, 1 is 1, 0. So you have 1 on over here. So 1, 0 is 1, 0, 1 is 1, 1, 0 is 1, 1, 1 is 0, 1. So you have to carry 1 over here. So here is 1. Then 1, 1 is here is 0. But you have another 1, which is 1, 0 is the answer. So you bring the last bit to add to the first LSB lah, this significant bit. So this is your new add or new checksum. Okay, so then you can have your third bits over here. Okay, and then this is your fourth bit. Okay, and eventually after you have all these 4 bits, okay, or combination of bits, then you do the checksum. Okay, and then this is what you get. Okay, all right. Okay, so this is the checksum that you will use to send after you do what we call one's complement. Okay, complement. So basically what we are saying here is that you have this first message, you have 1 0 0 1 0 1 1 0 0 1 1, which is this one. Okay, then this is one block of message. Then you have this second block. Okay, so this is the second one, the third one, okay, and the fourth one over here. Okay, then you need to also send this with this checksum. Okay, so you have this block, first block, second block, third block, and fourth block, and then this is your checksum. Okay, So you send this through your transmission medium. So this is at the sender side, okay, and this is at the receiver side, receiver. So at the receiver side, you have to do the same thing, whereby all these numbers that you receive, okay, say that this you don't have any error during the transmission. So you do the same technique that we have just now. This first message, okay. So you put it over here, okay, and you sum it up with this part, okay. So you have this numbers, right? And then you have the third one, okay, and finally the fourth one. So with respect to that, you will see that if you sum this up, if it give you all ones, okay, all ones, all ones. So the next thing is if you to do the ones complement, then you change it to everything from 1 to 0. Okay, so for those who did not can't recall what is ones complement, the ones complement method means that whatever the bits that you have to change it. Okay, so the attendance link, I did not put it yet. Let me check. I have shared the on the QR code. Okay, let me just copy this and then put it here. All right. So coming back to our discussion, okay. So for the checksum, okay. So basically, what we would like to have is that we would like to make sure that whenever we do this one's complement, okay, you will have all zeros, meaning that there's no error, okay. And the one's complement, for those who did not recall, is that when you have any bits, so when you do one's complement, you just change the number of bit from 1 to 0, 0 to 1. Okay. So like here, if the sum is all ones, then it will, when you do one's complement, you will have all zeros. Okay. So same goes as here. Okay. When you have all the sum is 1, 0, 0, 1, 1, 1, 1. So when you do the first one's complement, you change the 1 into 0, 0 into 1. Okay. So with respect to this, so you can either identify it's an error message or not. Okay, so perhaps by doing this, you will already know either it is an error message or not. Okay, traditionally you can see that the internet has used 16-bit checksum. Okay, where the message is divided into 16 bits word, meaning that if you have a whole bunch of information that you want to send, okay, so if this is the whole message that you want to send, okay, so what you need to do is that you have to separate it into some blocks, okay, and this block represents 16 bits, okay. So this long is 16-bit, then another 16-bit, right? And the value of the checksum word is initially set to zeros, okay? And all words include the checksum are added using one complements addition, okay? Use the same example that we have on this part, but now instead of 8 bits, they are using 16-bit, okay? So the sum is complement and becomes the checksum, and the checksum is sent with the data, okay? So after you have done the sum of all these bits, okay, and then you need to add another bits for your checksum, and then you send it to the receiver. Okay, so at the receiver end, okay, you do the backward process, okay, where actually not the backward. I mean, you use the same technique. Okay, so you just add all the bits. Okay, so the message and the checksum is received. The message is divided into 6 bit of word. Okay, and all words are added using one's complement addition. And the one that we want to identify is that if the value of checksum is 0, the message is accepted. Okay, otherwise it's rejected. So with checksum, you either detect or you are unable to detect the error. So if how do you detect the error is that when you do the checksum and then once complement, and if you receive all the signal with zero checksum, so you will say that this is a good message, or there's no error with this message. Okay, otherwise you have to reject. So it's either you accept or you reject for the checksum, right? Okay, so these are the flows lah. So basically the same thing. Okay, so the algorithm to calculate the traditional checksum, word and checksum are each 6 bit, but sum is 32 bits. Okay, left sum can be found by shifting sum. So this is the technique. If you can understand how it is being done, then you are okay with the checksum implementation. Okay, so to as a summary for the checksum means that you have to sum all the block of messages. Okay, then you have to do once complement. Okay, so add the checksum that already have what the once complement, and you send to the receiver. Okay, and the receiver side. Okay, so you do the same technique where you sum all the block again, and if you receive it all once, okay, or after you sum everything as all once, you can see that everything is okay. Okay, and you can accept the message, right? So in other or if in others implementation, they will also use kind of what they call it, uh, not one by one. So if I have this message again, okay, so say that just now we have 1000011 123412341. Okay, so this is the first message first, then 1101011. This can be the second message. The technique that they use just now is where you add one by one. But if you have four blocks, okay, so this is an example: 0110111. So this is the third block, okay, third block, and say that 1000111. Okay, and this is the fourth block. So what you can do if you get this kind of question, okay, you can just either you can add one by one, or you can have this kind of arrangement where you can do this with XOR, okay, and you can sum it up, okay, so sum it up and you can actually receive the message according to what they have, right? So this is another method that perhaps you can use later on. But from this slide or from this discussion, you sum one by one, and then you can move forward with respect to that checksum. Okay, right. So that is for error detection, right? Now, other than for error detection, we can also have what we call error correction. So, in error correction, basically the first method or the things that we need to do is that we have to detect if there's any error or not. So, if there's any error, so what we need to do is do the correction. So, you need to have some basic how you want to make the correction. Okay. So one of the techniques here is what we call forward error correction. Okay, so basically it says that here that the error detection is a useful techniques, but found in data link layers such as HDLC and in transport protocols such as TCP. Basically, you want to detect, okay, the error. Okay, but if in a simple detection, you after you detect, what you need to do is that you have to retransmit. Okay, but with retransmission, meaning that you have to wait for some additional time, which basically for wireless communication, for long haul communication, it is not a proper way to deliver. So with respect to this, you can see that for properties of your transmission, like for instance, the bit error rate means that it can increase, okay, so quite high, and result in large number of retransmission. Okay, so with this retransmission, yes, you can detect and you can make correction, but it's not an optimum process for wireless communication or for long distance communication. Okay, so here it says that propagation delay is very long compared to the transmission time of a single frame. So it's okay to detect and do retransmission, but and another example here is that for real time, then for real time also is not a good one. So we need to correct the error and reproduce the packet immediately. Okay. So rather than detect, you need to detect and also you need to make correction. So need to correct errors on basis of bit received. So a forward error correction is a way of adding redundancy. Okay, so the keyword here is redundancy to the message, so that the receiver can both detect and correct common error. Okay, again, detection over here might not be proper, okay, but at least you can detect and you will correct whatever some common errors that can be detected lah, okay, but not everything can be detected directly. Okay, so on the transmission end, each k bit block of data is mapped into n bit block, okay, which n is greater than the k, so called a code word using the forward error correction encoder. Okay, the code word is then be transmitted. Okay, so the idea here is that you need to have additional what we call redundancy message, similar to for the error detection that we already seen on just now and also from our previous slide or previous lecture. So, but here it's not just detect, but it's way forward to also make correction. Okay, so this diagram should on the transmission side and at the receiver side, if you have k datas, okay, and then you need to put it into your forward error correction encoder, okay, and then these n bits, okay, is being transmit, okay, and at the receiving part, okay, so the code word is being fed into the FEC decoder, and then there's two solution for it is that if it's being error, okay, and cannot be corrected, so you will actually drop this packet. Okay, but if you have the message accordingly, so you accept the packet and the data will send to the upper layer. Okay, so there are four different scenarios from this, as I mentioned. The proper one is or the main one is with no errors. Okay, so if you put it into the FEC decoder, okay, and you found that is identical to the original code word, then the data block can be accepted as an output. Okay, then you also have the second scenario, okay, where you can detect, okay, and you can make correction, okay, because as mentioned that not every errors can be detected. For instance, perhaps the detection can only support for few bits of error detection. Okay, so then if it's more than the one that expected to be detected, then you will have an error that cannot be corrected. Okay, so for certain error pattern, it is possible for the decoder to detect and correct those errors. Thus, even though the incoming block differs from the transmitted code word, the FCC decoder is able to map this block into the original data block. Okay, so you'll see later how this can be presented. Okay, where you can actually detect and then also make correction. Okay, so in Hamming coding also we'll already seen that you can actually detect and you can identify where is the error within the bits from your message that being transmitted. Okay. The third scenario is that you detect but you unable to correct. Okay, so for certain error pattern, the decoder can detect but not correct the errors. Okay, so in this case, the decoder simply reports an uncorrected error. So now this one you process and it's okay and you accept. This one you process and you find there's an error, then you make correction. Okay, but for this one you process and you detect then an error, then you inform the sender that there's an error. Okay, so here what you need to do is retransmit lah. Okay, although we that is not the best option, but now because you are unable to correct it, so you have to retransmit. Okay, and the fourth one, you are unable to detect. Okay, typical rare error types, the decoder does not detect the error and maps the incoming n bits and data block into k block and differs from the original k bits block. Okay, so this one you unable to do anything because you first of all you unable to detect there's an error. Okay, so with respect to that, you still accept it, but with your blindness lah, without having any information that this is incorrect message. Okay, so these are way the scenario that you can see lah from the forward error correction process, right? So next thing is that we also have the Hamming code correction, where in Hamming code correction or code word, basically what we need to do is that we have to add additional bits, okay, so that you're able to send it with respect to the actual messages, okay, and then you can identify what would be the basic what do you call it information, okay, with respect to that. Okay, so this is for the Hamming code distance. Okay, so a code word is mapped from k bit data sequence to n bit code word with n must be greater than k. Okay, so now the code word is must be greater than the information that need to be sent. Okay, so the code rate should be k is equals to k divided by n, but it's much more, it should be smaller than 1, right? So in this example, your k, your data block, n should be, k is 2, okay? Your k is equals to 2, your n is equals to 5, okay? And your r is equals to 2 over 5, right? Okay, and this is less than 1, then this should be okay lah. So now you have your data block, which is only 2 bits, but your code word is 5 bits. Okay, this is 5, this is 2. Okay, so the data block is your k, and your code word is your n over here, right? So you can see that you have to add more bits compared to the actual bits that you want to send. Okay. So assumption here, the transmitter and the receiver both knows the code word. So now you have to do some assumption that both sender and receiver will know the code word. Okay, so that's the assumption. Okay. The transmitter takes data block, maps them into code word and transmit the code word, not the data block. Okay, and the receiver receive the code word, okay, and maps them back to the data block. Okay, so this is what you will see on the implementation of this Hamming distance. Okay, the idea here is to have a very minimum distance between those code word. Okay, so the error correction, okay, capability of a code block is directly related to the Hamming distance between each of the code words. Okay, so later you will see that we would like to have this distance as minimum as we can. Okay, so how do you define or how do you do this? This is the simplest, simply the number of bit, which is V1 and V2 are different. Okay. So here an example, if you have 0, 1, 1, 0, 1, 1 for V1 and 0, 1, 1, 0, 0, 0, 1. Okay. You do an XOR of this code word, right? And XOR means that you need to have your A, B, and X over here, where you have 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1. When you have this, you have 0 over here. 0, 1, you have 1, 1, 0, you have 1, and 1, 1, you have 0. This is XOR. Okay, so that is why when you have this 0, 1, 1, 0, 1, 1, you XOR. XOR is something like this. Okay, 1, 1, 0, 0, 0, 1. So if 1, 1, you have 0, 1, 0, 1, 0, 0 is 0, 1, 0 is 1, 1, 1 is 0, 1, 0 is 1. Okay, so you receive this. Okay, and now if you what they call it, hence the Darwin distance. Okay, so we can say that the distance between it is 3. Okay, so how do how did they get it? Is that they sum these numbers lah. So you have 1 bits, 2 bits, and 3 bits. Okay, so you have the 3 distance lah. Okay, so you want to find what is the mean. Okay, so the next slide shows you. Okay, say that this is an example where you have again the 5 to code. Okay, now your block and the code word is being represented. So both of your sender and receiver should know this. TX and RX should know this. Okay, so with respect to that, you have to compare lah. Say that between this V1 and V2. Okay, so you have V1 and V2. So 0, 0, 0, 0, 0, and 0, 0, 1, 1, 1. You do XOR of this. Okay, so you get 1, 1, 1, 0, 0. So with respect to this, you know that this is a 3. Okay. How about this? V2 and V3. So V2 and V3. V2 is 0, 0, 1, 1, 1. And V3 is 1, 1, 0, 0, 1. Okay, so 1, 0, 1, 1 is 0, 1, 1, 1, 1. Okay, so now you have 4 distance between it. Okay, so now you can see that you can actually compare all the distances, okay, with respect to this 1 by 1 code word. Okay, so these are the values. Okay, 3, 3, 4, 4, 3, 3. Okay, so we can say that the minimum is 3 lah over here, because you have 3 as the very minimum values. Okay, so we want to have d min to be large, okay, and the radiusy to be small. So d min to be large and the radiusy to be small. Okay, right. So here again, when at the receiving part, okay, the transmitter send a data block 00 using code 52 code block, and it gets coded at 0000. Okay, so and send through. Okay, so you wanted to send this 00 data code, okay, data block, and you actually send the 0000. Okay, so here it says that you send it exactly the 00 data block with this code word. Okay, this one is correct. But then suppose that the output of the channel is now changed between 0000 to 0010, meaning that this bit has already been changed. Okay, so one bit received in error, and this is not a valid code word and should be what should be the receiver do. Okay, so you will see that with this Hamming code, it can be detect where is the location of the error. Okay, so we'll see it thoroughly. So when an invalid code is received, the receiver should choose the valid code word using the minimum distance to the invalid code. So if we receive the 00100, so we have to compare it with B1, B2, B3, and B4 based on this diagram, right? So now, say that you want to compare B1, so 00100 using this XOR, okay, which is the B1 is 00000. So you have 00100. Okay. So now your distance, minimum distance is 1. Okay. Then you have 2, 3, 2, 4, and 3. Okay. So from this we can see that we know that the minimum one is 1. Okay. So hence we should pick code word of B1. Okay. So basically, okay, it's not just what they call it. If you see other method of how this Hamming code is being defined, okay, it will also identify the actual error is this bit, okay. But using this method of description, you can see that it's just detect that rather than you compare this all the different code, and you see that this is the very minimum value, okay. So with respect to that, you choose V1 as your output. So directly, when you say that this is the very minimum distance between all the codes to this info message, okay. So what you can do is that you instead of you receive it as 0100100, okay, with an error, so you will see that actually you have to change it is to 00000. Okay, so then you pass this to the upper layer to be processed. So here it says that hence we should pick code word V1. The receiver then decodes this the code word as data block 00, and the data is correctly received. Okay, so now you have make correction towards the data that being sent errorly. Okay, so this 5 to code can always correct code word received with one error. Okay, so here you can see that you can only have one error being detected for this code word. Okay, but the number of bits that you can need to add is 3 bits additional to the actual data that only have 2 bits. Okay, so it actually not efficient, but it will do for detection. Okay, and this one there's you can use forward error correction using XOR. Okay, meaning that you can do the XOR and you can detect either there's any error or not from that messages, right? The third implementation is what we call chunk interleaving. Okay, so say that you have all these messages that you want to send, and you put it into 5 packets. Okay, so now you have all these few messages, okay, that you want to send. Then you when you send, okay, on your transport layer, okay, rather than you have to send everything, you put it into packets. Okay, so now you have 5 packets altogether. Okay, and say this is your packet number 1, packet number 2, packet number 3, 4, and 5. So now rather than you send directly to the medium of transfer, what you can do is that you can pack this or you can make what they call a chunk interleave, okay, out of this packet. So what you need to do is that rather than you send this whole stream one by one, what you can do is that you stream this, okay, one by one horizontally. Okay, okay, so you have this 0, 1, 0, 6, 11, 16, 21. So 0, 1, 0, 6, 11, 21. So instead of sending directly this bit, now you have to take each and every first bits from each frame, okay, and then you group it together, okay, and then you send this as your first bits that being sent. Okay, so this is your new packet 1. Okay, so this is the new packet 1. that actually combine all this horizontally, right? So packet number 2 will be taken from this horizontal, packet number 3, 4, and packet number 5, right? So you send this, okay, and if unfortunately this packet 3 lost, okay, so here the representation that this packet lost, okay, so when you receive this, you can see that rather than this whole message say that packet 3, supposedly that if we send it packet by packet, this packet 3, instead of the combined child interleaving here is being lost, so you will lost this whole packet, but instead you are having some bits of the message for each and every packet. So with respect to that, you will see that you have some intervention where with this kind of arrangement, when you receive the packet, so you see that only 1 out of 5 bits that being lost. Okay, so then this one should be much better to be used lah. Okay, so here it says that another way to achieve efficiency in multimedia is to allow some small chunk to be missing in the receiver. Okay, we cannot afford to let all the chunk belonging to the same packet be missing. However, we can afford to let one chunk be missing in each packet. Okay, so this example is when you do some video transmission, okay, or video streaming, whereby you can, out of all the packets that you being sent, okay, basically some of it is just like a still image rather than a transition. Okay, so when you have this missing part, okay, so perhaps just 1 bits of your transmission, say that this is your screen, TV screen. Okay, so all this bit perhaps is being filled with this bit. Okay, so now if you have this part of missing, perhaps this is the only part that being missed. Okay, the rest you can see. Okay, so this one is still acceptable lah. Okay, although we need to have this a proper, all being proper being transmit. Okay, but at least you still have some what they call it, display that being able, although this part of bit is currently being missing. Okay, so this is what we call chunk interleaving, right? The next part of implementation is what we call compounding. Okay, so this method basically is that like when you see YouTube, right? Sometimes you have low resolution and high resolution image, like high resolution. Okay, so now what we do is that we tend to have both this high and low resolution of your YouTube, for instance. Okay, so we start with all the packets with using high resolution. Okay, so you have the P1 until P5 with high resolution, and then you also send on the second packets, okay, with this low resolution, right? So now you can see that for the first packet that being sent, this one is empty because you don't have any yet, because this is the first packet that being sent. So you send this packet, okay, with this compounding packet, which is the low resolution of the previous packet lah. Okay, so since there's no different other packet of frame, okay, over here, so that we put it empty lah. But let's look here on packet 2, you can see that you will need to send the P2 high, okay, with the high resolution plus with the low resolution. Okay, so later we'll see at the receiver how this can help to actually prevent a kind of stop of frame in your video sending lah. Okay, so you do the same thing for the rest. Okay, so you have P3 high resolution add on to P2 with low resolution and so forth. Okay, so you send packet by packet, and say that this is a scenario where packet 2 lost. Okay, so packet 2 lost. Okay, how do you recover? Okay, instead of you have to resend back, you know that the next packet that it received, okay, can be what they call it, as a what they call, you can get the low resolution from the next packet. Okay, so say that here packet 1 no problem, so you have you will play the high resolution. Packet 2 lost. Okay, so instead of this empty frame, okay, so what you can do, you wait for packet 3 and you play your packet 2 with low resolution. Okay, so in what they call, in some video transmission or streaming, sometimes you need to delay the playback. Okay, say that you have 8 seconds of playback. Okay, so when you send this, okay, and you didn't receive this, and this one can be received before the 8 second. Okay, so you can add the P2 low to your second part, and then you can actually display it to your audience. Okay, so this can help to perhaps rather than send show empty frame, so you have low resolution. Okay, and then the next frame you receive the high resolution and so forth. Okay, so this is a forward error correction where you can use this to quickly correct if there's a missing frame or package. Okay, so this is the compounding technique, right? So from this slide, from this chapter, so basically we have seen a single bit error and bursty error, where a single bit error, you have 1 bits that are being missing or error. A burst error means that more than 1 bit. Okay, and most of the detection is mostly can detect a single bit error. Bursty error will have to do some other method. Okay, and then there's a different type of method. Okay, so that can be used. Okay, if you can remember also the one that I mentioned, that for error detection, okay, so you can have 4 different methods. Okay, the first one is what we call parity. Okay, parity check. Okay, then the second one we call two dimension parity, two dimensional parity. Then we have the CRC, cyclic redundancy check, and finally you have the checksum. Okay, for the error correction, we'll see later on different method of error detection. Okay, then we also have seen the Hamming distance, the chunk interleaving, and compounding for the forward error correction method, right? So do you have any questions so far? Are you still with me? Sorry, I cannot show the video. Something error with my PC. So I'm not so sure. Is it okay? Right? So if there's no question, I would like to move to the second or the next lecture. Okay, which is what is it? Let me change to the slide. Okay, so the next slide, okay, on lecture 5A, data link layer, right? Okay, so for this chapter, subchapter lah basically. So what we would like to know is more understanding on the data link control. Okay, why do we need this? Because we need to have a reliable and efficient data transmission. Okay, then another method that we need to have is what we call flow control. Okay, so for reliable transmission, so we need these two lah. What we call error control, and also flow control. Okay, what's the difference between these two? Error control, when you detect error and how you manage if you receive the information with an error. Flow control is basically how you make sure that the transmission can be sent, okay, with the acceptable data rate of your receiver or perhaps the medium of transfer. Okay, so when we talk about flow control, the amount of generation, if you have your sender TX and your RX receiver over here, then you have your medium. So you generate packet, right? Packets, and this packet being sent to here. But say that you generate over here is 100 Mbps, megabit per second, but for your data link it only accept 10 Mbps, meaning that rather than you can send directly one packet or 1 Mbps message, okay, to your data link layer, okay, or the medium of transfer over here, basically you have to wait 10 times, okay, to so that it able to do this process, okay. And at the receiver side, perhaps also is the same as the transmitter, then it can accept 100 Mbps. There's no problem. But here, the bottleneck would be your transmission medium. Okay, so the question here: how do you make sure that this message that being generated on the transmitter doesn't overwhelm either your medium of transfer or actually the receiver? Okay, so that's the question with the flow control. So here in this chapter, we will see flow and error control, where we want to prevent the data overload and integrity. Data overload here means that there's too much message that need to be sent, but it cannot be support. Okay, so rather than you receive it and you drop everything, okay, and then you retransmit, it will be much better if you can say to the sender, hey, wait for for some period of time, and you can send after this. Okay, that kind of conversation lah, and integrity. Okay, then differentiate the use of various automatic request, repeat requests for flow and error control. Okay, so we'll see a different type, like for this automatic ARQ, where you use like a stop and wait protocol, or perhaps we'll also see some other protocol that Windows sliding protocol and so forth. Okay, and finally explain the implementation of HDLC, high level data link control, for synchronous data transfer, right? Okay, so we will see on the flow and error control, okay, and then stop and wait ARQ, okay, and then the HLDC, where you see the configuration, frame format, control display, and data transparency or bit stuffing. Okay, right. So data link basically is designed for what we call node-to-node communication, lah, right? So you have the say that your IP address, okay. So this is the 5 layers, okay, and this is the medium, okay, and then this is your end receiver, okay. This is the RX, this is the transmitter TX, okay. In between, you have your nodes, network nodes, right? Okay, which can expand to 3 layers until the IP layer. Okay, so for the data link, you have the MAC address. Okay, MAC address, and every of each device here has a unique MAC address. So when it says that it's a node-to-node communication, means that it's on the data link layer level that communicate between one device to another device. Okay, so the process node to node is when you send from this part to this network guy. Okay, and then the next process is between this network guy to this network guy. Then you also need to communicate between this network guy to this network guy, and finally this network guy to the end receiver, right? So that means that node to node. when you talk about point to point, okay, it means that it goes from here to here. This is a point to point. Okay, node to node means that you have to process it and make sure that it is being transmitted from this node to the next node and so forth. Okay, so the most important responsibility of the data link layer are flow and error control, and collectively these functions are known as a data link control. Okay, so this combination is called a data link control, where you have the flow and error control being combined together. Okay, so the word flow control, as mentioned just now, when you are trying to send and you overwhelm the medium of transfer or the receiver. Okay, so any receiving device has its limits. It's not just the receiving device, but also the intermediate device. It has the limit speed at which it can process incoming data and a limit amount of memory in which to store incoming data. So here, this storage is usually what we call your buffer lah, buffer. Okay, so your buffer is has limitation. Okay, the size. So you have a limitation of size for your buffer. So with respect to your flow control, when you send too much, okay, there's a possibility that it cannot process on the processing part, and also sometimes it's your buffer also will be overflow. Okay, so when this happen, basically the one that we can do is that we drop the packet. Okay, so when we drop the packet, it's time to resend. Okay, so if the same thing happen over and over again, okay, so it can be compound again, then the whole message will actually collapse lah. Okay, so the flow control has to make some sense so that you're able to make sure that there is not overwhelm the intermediate device and also the final device. Okay, the receiving device must be able to inform the sending device before those limits are reached, and to request that the transmitting device can send few frame or stop temporarily. Okay, so how do you do this? Is that the receiver or the medium device, okay, what they need to do is that they need to inform the one that generating the packet, so that either you send it lesser, okay, lesser or fewer, or you need to stop it temporarily. Okay, so that is the function of this flow control. It needs to identify that the packet is being transmit too much. Okay, and then you need to also have the medium intermediate device or the end receiver that the one inform the generated transmitter that the message either need to be send fewer or stop it for a while, and then send it when the traffic is already okay. Okay, so the flow control refer to the set of procedures. Okay, so how do you represent this? Okay, so that you're able to make sure that the message that being sent is not too much to be processed. So procedure used to restrict the amount of data that the sender can send before waiting for acknowledgement. Okay, so the term here, you need to, is a procedure. You restrict the amount data can be sent while waiting for the acknowledgement. So what is this acknowledgement? You see later that when you send a packet from sender to receiver, the receiver will actually send another message called ACK. I also have mentioned about this. ACK acknowledgement or NACK negative acknowledgement can be sent from the receiver part to the sender to identify this is a positive acknowledgement and this is a negative acknowledgement, right? So means that usually the positive means that okay, you can send the next packet, or negative ACK is where you can say that I didn't receive it. Can you resend? Okay, so this is the way the computer receiver communicate with the sender by having this acknowledgement and negative acknowledgement. Okay, so for error control, you need both lah, error detection and error correction. Okay, so both error you have to detect and perhaps you need to make correction if possible lah. Okay, so it allows the receiver to inform the sender any frame loss or damage in transmission and coordinate the retransmission of the frame by the sender. Okay, so the very basic as mentioned is retransmission lah, but if you able to send forward error correction, like where you have additional chunk to be sent, or perhaps you can put an bit interleaving, sorry, not bit interleaving, forward error correction lah method, so that you're able to correct the message without have to be retransmit, then much better. Okay. So error control in the detailing layer is often implemented simply. Anytime an error is detected or in an exchange, a specified frame are retransmitted, and this process is called automatic repeat request. Okay, so ARQ is a automatic repeat request. Okay, the one that we do in our lab is different. This is that one is apa lah tak ingat, for mapping between your IP address with your MAC address. Okay, this is different. Okay, so don't mix up. Okay, so this one where you can implement it in detailing layer, when anytime any errors is detected, okay, specific frame are retransmitted in order to make sure that you receive the message with error, without any error. So error control in detailing layer is based on automatic repeat request, which is the retransmission of data. Okay, so the basic one is by having this packet when it's being detected as an error, so you have to retransmit. Okay. Then you can improve it, okay, by having what we call stop and wait ARQ. Okay. So in the stop and wait is the simplest flow and error control mechanism, which has the following feature. When the error correction in stop and wait is done, okay, by keeping a copy of the send frame and retransmitting of the frame when the time expired. Okay, so you have one thing that we have in our transmission, what we call TTL, time to live. Say that your TTL is 180 millisecond. Okay, it means that when you have a sender and a receiver, something like this, this is your RX, ATX transmitter, this is your RX. Okay, so when you send a message, frame number 1, okay, from sender to receiver, and here you start your time countdown lah, TTL. Okay, so if you don't receive within this period of time any acknowledgement from the receiver, so what you can do that you will resend it back. Okay, so this is your F1 again. Okay, so here it says that the sending device keep the copy of the last frame, transmit until it receive an acknowledgement for the frame. So when this receive, okay, and you acknowledge this, right, ACK here, then the receiver will process it lah when it's acknowledged. Okay, when you know that it sends the second frame. Okay, so keep a copy allows the sender to retransmit loss of damaged frame until they receive correctly. Okay, sorry. So here it says that sending device. Okay, so the sending device here, when they send, what they can do is that they have a buffer over here, sender buffer. So the buffer would be something like this lah. Okay, so you have kind of a buffer where you have information that being sent. So you save this part of the frame 1 to be transmit, and if not being acknowledged after the time to live, okay, so you retransmit. So meaning that you don't have to regenerate it at the at the processing part lah. So you just need at the sender part. Okay, so the sending device keep a copy of the last frame transmitted, okay, until it receive the acknowledgement. When you receive the acknowledgement, then you can drop this packet, okay, and so forth. Okay, so keeping a copy allows the sender to retransmit lost or damaged message until they are received correctly. So you don't have to regenerate this. Okay, so for this uh, error correction and detection, so you have two different channels. Okay, so you have the noiseless channel, okay, where you have the simplest and stop and wait, okay, and also you have a noisy channel, okay, where you can see that you have few of this option, where this one based on the stop and wait ARQ, okay, but then you have the go back end and the selective repeat, okay. So this idea basically is that for the first one is that when you have a packet to be sent, you wait for the acknowledgement, okay, and then the sender can discard the packet, okay, and the receiver can process the packet at the receiving end, okay, and then send the next packet, okay. So that stop and wait. Go back end basically later you see that you can actually send multiple packet based on what we call sliding windows protocol. Sliding windows protocol. Okay, so you will want to send multiple packets at one go and acknowledge everything at one go also. So with this sliding windows protocol, so you can implement this go back end, and also you can do with this sliding window protocol, so you can use this selective repeat. So go back end means that later you'll see that with this one, if the packet what they call it, more than the packet that have an error, has what they call an error, so it will send everything back lah. But with this selective repeat, you only send those who packet that only lost during the transmission. Okay, but we'll see that later on lah. So we have this simplest stop and wait. Simplest is where just now we say that you just retransmit. Stop and wait, where you have to wait for the acknowledgement, okay, and the stop and wait ARQ basically where you have the TTL, okay. Okay, so the stop and wait ARQ, okay, for identification purpose, both data frame and acknowledgement frame are numbered alternatively 0 and 1, okay. So you just have this 0 and 1 on your acknowledgement, okay. So your acknowledgement can either be 0 or 1. Okay, so this is what being implemented in the stop and wait ARQ. Okay, so when you send a data frame 0, okay, and is accomplished by an act 1 frame. Okay, so when you send frame 0, you will send an 1 frame, acknowledge 1, okay, indicating that the receiver has received data frame 0 and is expecting the data frame 1, right? Okay, and this number allows for identification of data frame in case of duplicate transmission, important in the case of lost acknowledgement and delay acknowledgement. But you limit to 0 and 1, okay. The next frame will acknowledge 0, then acknowledge 1, and so forth. Okay, but it doesn't count up lah. It's just have 0 and 1. So a damaged or lost frame is treated in the same manner by the receiver. If the receiver detect an error in the received frame, it simply discard the frame and send no acknowledgement. Okay, and if the receiver receive a frame that is out of order, 0 instead of 1 or 1 instead of 0, it knows that a frame is lost. It discard the out of order frame. So basically here, it can, if it's an error, okay, it simply discard and you don't send any acknowledgement. Okay, so after the TTL, so the sender will resend back the same frame that did not receive the acknowledgement, right? or if it receive a frame with which of that or out of order, okay. So instead of you should is frame 0, then acknowledge 1, you receive acknowledge 0, meaning that it is out of order, so you can discard the frame again. So the sender has a control variable which we call S, that holds the number of recently sent frame 0 or 1, and the receiver has a control variable which we call R, which hold the number of frame expected 0 or 1. So you just have 0 and 1, and the sender start a timer when it sends a frame. Okay, so this is the TTL one. Okay, time to leave, TL. And if an acknowledgement is not received within the allocated time, okay, so if not received, okay, it assume loss, and then we resend it. Okay, and the receiver send only positive acknowledgement for the frame received safe and sound. Okay, so you just send a positive acknowledgement. Okay, or else if it doesn't, if you detect error, so you don't send any acknowledgement. Okay, and it needs to wait for the TTL so that it is able to resend it back. So it is silent about the frame damage or loss and wait for the TTL and then resend it. Okay, so the acknowledgement numbers always define the number of the next expected frame. If frame 0 is received, acknowledge is 1 is sent. If frame 1 is received, acknowledge 0 is sent. Okay, so this diagram will show you the different situation for normal operation when the frame loss, the acknowledgement loss, and the acknowledgement is delayed. Okay, so this view diagram. Okay, so the one that I've mentioned to you just now. Okay, so this is what we call timing diagram. Okay, so perhaps what you can see is that this is the medium lah. Okay, this is the transmission. Okay, and it can go to and forth between sender and receiver. Okay, and this represent the delay lah. Okay, if you have a dotted line, this is the delay, transmission delay. Okay, transmission TX delay. Okay, this is the timing, the timing over here. Then this one is the delay for the acknowledgement. Okay, so this one is the delay. Okay, the time. Okay, because this is the time. Going horizontally down here is increasing of time. Okay, so now say that this is time 1. Okay, this is time 3. This is time 4. For instance. Okay, so the increase in time. Okay, and the sender and receiver keep the 0 and 1. So here, when the sender send frame 0, right, the receiver will acknowledge with 1. Okay, then the sender send frame 1 and acknowledge 0 and repeat it again. So it just have 0 or 1. Okay, because if it doesn't receive the packet acknowledgement, it will keep sending. Okay, so this is the basic one where you send frame 0, you acknowledge 1, frame 1 acknowledge 0, then frame 0 again acknowledge 1, and so forth. Okay, so you repeat it until the end of your transmission. Okay, so this is the normal operation. So no problem lah. Okay, then if there's a frame loss over here, okay, so now you have this frame loss. Okay, so you send acknowledge 1 when you receive frame 0. Okay, and then the sender will say that, hey, I received acknowledge 1, so I need to send frame number 1. Okay, and start timing. Okay, and every time here is also have the start this TTL, start timing. Okay, but within the period of acceptable TTL, it receive the acknowledgement, then it sends the next one. But here, since you don't receive it after you time out, what you need to do is you resend your frame 1 again. Okay, so anything we don't know what happened over here, but we don't receive or the sender doesn't receive the frame, and you don't actually have this acknowledgement. So basically, the sender doesn't know lah, either the frame loss in transmission or its acknowledgement problem or whatsoever. but after some time it doesn't receive the acknowledgement, which is next one is acknowledgement 0, so it will resend it back. So it resend and receive the acknowledgement, then you can send the next frame. Okay, so this is when the frame is lost. Okay, then here is when you have the acknowledgement loss. Okay, just now is the frame loss, now is the acknowledgement loss. So the same thing happened. You have the timeout, the TTL over here, start when you send your frame and it doesn't receive it. Okay, so it will resend it after the time is out. Okay, so here you can see that you doesn't receive the frame one, so you acknowledge after you receive frame one, you acknowledge frame 0. Okay, so expecting frame 0, frame 1 is discarded. Okay, so here is discard because you don't receive or you what they call it, you receive a new one. Okay, then you will use this one lah. Okay, the one that sent, this one will be dropped lah. Okay, at the buffer, and this one will be accept. Okay. Okay, so this is acknowledgement is lost. Okay, same thing between these two, based on the timeout lah. Okay, if it doesn't receive the acknowledgement during the specific TTL time, so you will resend back the frame, right? And this one is when acknowledgement is delayed. So basically, frame 0, the receiver acknowledge, but then it received the sender back after the timeout. Okay, so that is why it says that acknowledgement is delayed. Okay, so when the frame is when the time is out, so the sender will see, oh, I didn't receive the acknowledgement packet, so it sends back the acknowledgement packet 0 lah. Okay, so sorry, the frame packet of 0. Okay, and then it sends the acknowledgement packet. It received the acknowledgement packet, and then it sends frame 1. Okay, and it's expected to have frame 1, but frame 1 lost in transmission. Okay, so this one also being discarded, then you need to resend your frame 1. Okay, so this is where you can see that the acknowledgement is delayed. Okay, so the timeout and the acknowledgement packet will need to sync together, right? So that are the 4 different scenarios where you have the stop and wait ARQ. Okay. Stop and wait ARQ can also be implemented in a bi-directional transmission. Okay, so here it mentioned that the bi-directional transmission, where previously is a unidirectional. So here you can use bi-directional, so it will be much faster. We can have bi-directional transmission if the two parties have 2 separate channels. Okay, so the terms that needs to be complied is that you have a full duplex transmission lah. So full duplex means that sender and receiver has 2 separate channels between sending and receiving. Okay, so that you can have this bi-directional transmission. So in this case, each party needs both S and R variables to track the frame sent and expected. Okay, so the word piggybacking over here is that it means that on the sending message, you can also append your ARQ lah. Okay, so piggybacking is a method of combined data frame. Okay, so it's a combined data frame with the acknowledgement. So this one is where you send the frame singly, okay, as a single one, and acknowledgement as a single one. But you can do both way where you combine both data frame and acknowledgement packet. So piggybacking, okay, so what the advantage is to the save bandwidth. Okay, so because the overhead for the data frame and acknowledgement frame, okay, can be combined in just one frame. Okay, so again also is to save time lah. Okay, so other than save bandwidth, also save time, right? So how do you do this? Okay, rather than the frame or acknowledgement being sent, so you send both, okay, in a single frame or a single transmission. You say that frame 0 acknowledge 0, meaning that it's try to acknowledge the previous one, but actually you don't have lah. Okay, so for example, figure below, station A and B both have data to send. Instead of sending separate ACK frames, station A sends a data frame that includes an acknowledge, so the term piggybacking here, and station B behave in similar manner. So it needs to detect what is your current what they call it, R0 or S0. Okay, same goes for here. Okay, it needs to identify or save it. So you send frame 0, acknowledge 0, then you can also send a frame 0. Okay, so means that this B can also send message to A. Okay, but with respect to the frame 0, so you acknowledge 1. Okay, and then frame 1, you acknowledge 1, meaning that you receive this message. Okay, and then frame 1 acknowledge 0, you are actually pointing to this one. So both are sending and receive, and it can also acknowledge on a bidirectional. Okay. Okay. The next protocol that we can use is what we call go back end, ARQ, and this being represented, okay, by what we call a sliding window protocol. Okay, so a sliding window protocol, basically you can have a frame that you can shift it to your direction of transfer lah. Okay, so say that here this is a frame of 1, 2, 3, 4, 5, 6, 7. So the sliding window over here is a sliding windows, okay, of 7 over here. So means that you have the 7, then you can shift it to the next frame. So this is the message that you want to send. Okay, but again, you can have these windows that being slide, so that you're able to further transmit within the specific period. Okay, so here, okay, you can, this is the send window, first outstanding frame, send window, next frame to be sent. So this is the next frame, this is the current frame. Okay, frames that cannot be sent, frames that can be sent but not received from upper layers, frame sent but not acknowledged, outstanding, frames already acknowledged. Okay, so this one, if it's done, okay, this part is already done. So we are focusing on here and moving forward. So here is the one that already being sent but not being acknowledged. Okay, so meaning that in the stop and wait just now, you send 1 and acknowledge 1, but here you can send 7 and you are waiting for 7 to be acknowledged. Okay, so that is what we start implement in sliding windows protocol. Okay, and this is the next frame. Okay, so to be expected. Okay, so this is on the sending side, sending side. Whereas for the sending window after sliding, okay, so after it's being slide, okay, so basically if you have knowledge 0, 1, and 2, okay, so you can move towards the next frame. So this is the one that need to be acknowledged, this is the one that needs to be sent lah, right? So now your windows can be moved 1, 4, 5, 6, 7. So until this one, okay, so these 3 can now be sent and wait for the acknowledgement of all these 3 also. Okay, so this is after being Windows sliding being sent. Okay, and then here frame already received and acknowledged is on this part. Okay, frames that cannot be received until the Windows slide is over here. Okay, receive window, next frame expected. So this is the RN. And this is after it's slide. Okay, so basically this is the just one lah, one frame, and this is the one that already being slide. Okay, and this shows you, okay, the whole timing lah. Okay, Again, you have the timeout, the TTL, okay, and you can send and receive data, okay, and your data frame has a sequence number. Just now you have only sequence of 0 and 1, right? But now you can have more than one, 0 and 1. So you have a sequence number to identify if you have more than one packet. Okay, and then you have acknowledgement numbers and so forth. Right. So here is the timing diagram. Again, this is your time. Going down is increasing in time. Okay. So you start by sending here the windows is 3. The windows is equal to 3 bits. Right? How do you know that? This because shaded one, the shaded one here represent that's 3. Okay, so you want to send your 0, okay, then you want to send your 1, and then your 2. Okay, so what happened here is that when you send your frame 0, okay, and the receiver will receive frame 0, okay, and it will acknowledge lah, okay, and then send frame 1, okay, and then it will move to 1 over here, receive frame 2 and move to frame 2, okay, and then if it doesn't receive, then it will time out, okay, meaning that this one, it doesn't receive the acknowledgement. So what needs to be done is that you send back the frame 0 over here, okay, but the windows here, it doesn't shift, you see. So it still maintains 0, 1, 2 until you have successfully transmit with a receive of acknowledgement of frame 1. Then you move to the 1, 2, 3. But now it's remain at 0, 1, 2. And after timeout, you don't receive the acknowledgement packet because the acknowledgement packet perhaps lost during transmission. So you have to resend a frame 0. Okay, so that's why you need to send frame 0. Okay, so now it has to wait for the third one lah. Okay, so this is for this scenario lah. On this scenario, you have 4, 0, 1, 2, 3. Okay, so Windows here, Windows that we use is equals to 4, right? And again, you send frame 0, frame 1, frame 2, frame 3, and you expect that it will give you an acknowledgement, right, after frame 3, okay? Rather than this and every bit over here has its time out, okay? Now you send this first part of your frame sliding windows, okay, and then you wait for acknowledgement. Okay, the timeout is much more faster than each and every one of the packets lah. Okay, so if it doesn't receive, then you have to resend frame 1 back. Okay, so go back end. Okay, so later you'll see that it means that if you acknowledge 0 and 1, the one that needs to resend frame 2 and the upcoming one lah. Okay. So another example over here, here is 8 lah. The Windows is 8 because you have the darker shade here. Windows is equals to 8. Okay. Send first outstanding frame, send window next frame to be sent. Okay, so this next window to be sent. So this one is 4 lah. Okay, but it this is a selective repeat. So a selective repeat means that you can within these windows, okay, you can acknowledge which one has been accepted and which one is not being accepted. Okay, so frame send but not acknowledged, frame that can be sent. Okay, so a windows of 8. Okay, that currently being discussed. Okay. So for a selective repeat, where the term selective repeat, it means that you don't have to retransmit any of the frame moving forward, okay, is have an error or not being acknowledged. Right here, when you see that this frame is not being accepted or acknowledged, what you can see that you just select. Okay, so the frame that can be received and stored for later delivery, color box already received. So out of this 8, okay, so you already this 4, 7, and 9 already received. So you have to retransmit this white one. Okay, need to retransmit. Okay, so if these 3 already submit, then the sliding windows will move to your right hand side. Okay. Okay, same thing. Okay, of where most of the time the ARQ for the selective repeat. Okay, so this is the scenario. So now you have the windows is equals to 2. Okay, so you send frame 0, frame 1, you didn't resave it after the timeout, so you resend frame 0. Okay, same as the previous one. And then here you have 3 slide windows. Windows is equal to 3. Okay, so you receive 1, receive 2, receive 3. Okay, then you move on. Okay, so the sliding window. But if you don't receive it, you retransmit it. Okay, so you need to retransmit the same information, right? Okay, and that will be about the sliding windows. Okay, as a summary, if I could just change mine to uh, okay, so if I can just, how do I move this? Right. So basically, what we have seen is that we have the um, sliding windows protocol. Okay, so we have the go back end sliding windows protocols. Okay, so the one we have is the simple ARQ just now. Let me check. Okay, so we have at the beginning here, we have the stop and wait protocol. Okay, we have the go back end and the set repeat. Okay, so how do you see this one? So you have the uh, stop and wait, stop and wait. Okay, then you have your go back end, go back end, and then finally you have the selective repeat. Okay, so this one is based on sliding windows protocol. Okay, and this one is just a simple send and receive. Okay, so if you have your sender and receiver, okay, so for stop and wait is where you have your frame 1 send, then you acknowledge uh, 1, okay, and so forth. The go back end is that where you have your sliding windows protocol, so you can send a few packets, okay, and then you can receive acknowledgement of this packet. So if you have 0, 1, 2, 3, okay, so this is your sender and this is your receiver, so you can just acknowledge actually the 3, okay, and then you can send the 4, 5, and 6, okay. Whereas for the selective repeat, basically the same thing, but says here that when you send, okay, only these two being received, okay. So you receive this one, you receive for the fourth one, but you have an error on the third one, okay. So what the selective repeat needs to do is that the next one that needs to be sent is number 3. So 1 is accepted, 2 being accepted and receive acknowledgement, 3 has an error, and 4 accepted. So you don't have to repeat 3 and 4, you just need to retransmit 3. Whereas here, if that 1 is okay, 3 is okay, but you have an error on 2, so you have to send 2 and 3. Okay, so that's the difference between go back and selective repeat. Okay, so and this uh, being used to make sure that you're able to transmit the information quickly and detect any transmission error. Okay, so this is what we have already seen on the sliding windows protocol and so forth lah. Okay, so based on this, you have this stop and wait ARQ. Okay, go back and also selective repeat. Okay. And the next thing is that on the HDLC, so now we already seen the concept of flow control and error control. Okay, so basically you have the data link layer control. Okay, so you also have what we call high level data link control, okay, which is the actual protocol designed to support both half duplex and full duplex communication over point to point and multi point links. Okay, so these are the actual protocols. Okay, the one that we mentioned just now is how you do flow control. Okay, but on the data link layer itself, okay, so you have the HDLC. Okay, so if this is your data link layer. So in your data link layer, you have HDLC and also your MAC address lah, right? So how the question is here, how does this HDLC be implemented in the data link layer? So the rest of the slide actually mention about how it is being designed. Okay, so implement ARQ mechanism as we discussed above. Okay, and we need to see how's the configuration, the transfer mode, the frames and control feed. Okay, so basically, if you want to see the actual information, perhaps you can try to use your Wireshark, okay, and goes to data link layer, and you can see all the specific parameter that being used here. Okay, so now for HDLC, here it says that two common modes of transmission. One is what we call normal response time. Okay, can be used for point to point and multi point. Okay, so a normal response mode. Okay, is a station configured is unbalanced. We have one primary station and multiple secondary station. Okay, so it can be point to point means that you have one primary and then multiple secondary. Or one primary to one secondary station, but you can also have the multi-point where you have one primary and multiple secondary, so it's a point multi-point. Okay, and also asynchronous balance mode. This link is a point to point. Okay, and each station can function as a primary and a secondary. Okay, so this is a point to point. Okay, whereas this is for multi-point. So basically, this multi-point used for to support end user. Okay, so when you have multi-point, usually for support end user, and for a point-to-point, basically it can be what we call backhaul. Okay, backhaul communication that connects between your end-to-end user. Okay, in between you have this. Okay, so you can use this NRM and ABM. So for ARM, in the sense that when you have your command, okay, it can be a point to point where you have one response, or you can have multi-point, your command and multi-point over here. So this part is for your back end lah. Basically is what we call for your control. Okay. The information can be sent using frame, but this also some control messages, meaning that when you communicate, send video or whatsoever, there's also some additional packet that can be sent to manage the sending of your video or voice. Okay, so this represent the back end control that you won't see it, but it's needful for your communication to process accordingly. Okay, and then you can have ABM. Okay, so both can be command and respond. Okay, on both way. Okay. And then HDOC also define the frame. Okay, so it define three different frame. Okay, you have the information frame. Okay, you have the, let me change. Okay, so you have the information frame over here. You have the supervisory frames and unnumbered frame. Okay, so what is this all about? Okay, it's too many things, right? So each type of the frame work as an envelope for the transmission of different type of messages. Okay, so here you can see that you have this different frame for different type of messages. It can be your control message or it can be your information message itself. So iframe are used to transport user data and control information relating to the user data. Okay, so anything to do with your user data, control is using iframe. Okay, and then sframe is used only to transport control information. Okay, so this is for your control information, and uframe reserved for system management, where information carried by uframe is intended for managing and link itself. Okay, so this is for your user data. The information that can be piggyback, and also this one is just for your control information, and this one is for reserve lah, if anything that you need to use later on. Okay, so the frame of this, okay, it doesn't for the S frame you see that there's no user information. User info, nothing. No user info. But for your the iframe, okay, you can have your user information and also some additional headers and trailers that we call here. Okay, so that this can be used for your user information, piggyback information on top of your user information. Okay, here is for just management. Okay, or for your control specific, doesn't have any user information. Same goes for here. Is this one is for management information if you need to manage or you need to send information between all the devices. Okay, so this is your U frame. Okay, so you can see that the I frame has the user information, the S frame doesn't have it, and the U frame also for control, but it's for more management information lah. Okay. Then within that you can see the flag field. Okay, so the for this HDLC, you have a 8-bit sequence with a bit pattern. Okay, so this is the pattern lah. It won't change. So basically, when you send all your information, okay, so your flag field at the beginning will have 0, 1, 1, 1, 1, 1, 1, 0, and at the end 0, 1, 1, 1, 1, 1, 1, 0. Okay, so meaning that this is to separate between this field and the next field or the previous field. Okay, so this is just for a flag field that needs to as a kind of a border lah. Okay, border between the successive frame. Okay, so here it says that to identify both the beginning and the end of the frame. So this is the beginning of your frame, and this is the end of your frame. Okay, so serve as a synchronous pattern for the receiver. In multi-frame transmission, the ending flag of one frame can serve as the beginning flag of the next frame. Okay, so this is how it is being identified. So here, the flag is actually over here. Okay, the yellow one, and here. Same goes for the S frame, and finally the U frame. Okay, so you have the flag. Then you have the address field. Okay, so now we are talking about this part, the address field. Okay, so the second field of HDFC frame, the contain the address, okay, of the second station that either the originator or the destination of frame or the station acting as secondary in the case of combined station. Then if a primary station creates a frame, it contains a two address. If a second creates a frame, it contains the from address, and the address field can be 1 byte or several byte long, depends on the need of the network. Okay, so this for the addresses, it can be either the address of the secondary station, okay, or perhaps if you are using both communication, you have the to and from address lah. Okay. One byte can be identified to 1 to 8 stations. So this address field, okay, the size will be 1 to 8 station or 1 byte, okay. Because so for a larger network require multiple bytes address field. If the address field is only 1 byte, the last bit is always a 1. Okay, and if the address is more than 1 byte, all bytes, but the last one will be end of 0. Only the last will end with 1. Okay, so this is just to mention if you have much more information than a single byte. Okay, and ending each termination byte with 0 indicates to the receiver. Okay, and the network that do not use primary or secondary information, such as internet, use two addressing field, the sender address and the receiver address. Okay, so for internet, they use sender and also the receiver address. Okay, and then you have other control field, okay, other frame. Okay, so control information and FCS field. So where is it? Control. Okay, you have the control, and you have the FCS, control, FCS, control, and FCF. Okay, so the control information and FCF field. Okay, so control field is just 1 or 2 byte segment. Okay, this is for your flow and error control. Okay, interpretation, the bit is being filled in different frame type. The information field contains the user data from the network layer or the network management. So this is the actual data that needs to be transmitted. Okay, piggyback with all the other management information. Okay, and the frame check sequence is the HDLC error detection field to check either any error from the frame itself. Okay. And then data transparency, the data field of the HDLC frame can carry text as well as non-text information. Okay, some message type can create problem during transmission. Example, if the data field of HDLC frame contains a pattern that is the same as the reserve flag. Okay, so this is the one that you do for border separation. Okay. The receiver interprets that sequence as the ending flag, and this is not correct. So the rest of the bit are assumed to belong to the next frame, which is not correct lah. So what you need to do is that we have what we call bit stuffing over here. Okay, so here if you have this same information, but it detects is actually the information sense. Okay, because we are talking about bits right now. 0 and 1, so you need to include this just to make sure that it's separate between the border and the rest. Okay, can I share the link again? I think this is the link. Okay, right, so the bit stuffing is to identify the difference between it. Okay, so this is how to make sure that the data is not being confused with the actual flag. Okay. So with three expectation, bit stuffing is required whenever 5-1 occurs consecutively. So when the bit sequence really is a flag, when the transmission is being aborted, and when the channel is idle. Okay, so these are the three different methods. Okay. So as a conclusion, okay, so we have seen how we can use flow control. So previously we mentioned about error control. Right now we have seen that we can use flow control. Okay, so with the flow control, you can use stop and wait, ARQ, go back and selective repeat or piggybacking. Okay, and then we also have seen the HDLC, high level data link control, the frame itself. So how do you manage it? How's the information being inserted into the HDLC, or what are the modes that being used to control the HDAC itself, right? So with that, I think that's the last slide. I open if you have any other question or anything that you want to discuss further. Okay, please do by now. As for your information, for next week, we will have a quiz during lecture. Okay, so this is the quiz 2 that being already been identified. Okay, for our subject. Okay, so for next week, please be prepared during lecture. The same thing as the quiz one previously. So make sure that you are prepared. The chapter I'll inform to you later on. Okay. But basically, we will test you on the latest chapter that we already covered. Okay. So there, question. What chapters? Basically, until this chapter. Okay. And from last time we chapter 1 to 3, right? So this one will be 4 and 5, right? So this will be until today lah. Okay. So for that next week. Today TTL 7L got online tutorial class. Yes, yes. Unfortunately, yes. Right. On another note is that for next week, we will have uh, a total online class for lecture session. Okay. Whereas for the tutorial for next week, the whole session that I manage, I will need to do a reshuffle, or I have to basically during the specific time that we have, I need to reschedule because I'll be going for a conference for the whole week, except for the lecture, maintain as it is. Okay. For the tutorial session, I will inform you on how we arrange for it. Okay. For TTL6 online also, TTL6, TTL6L for next week. Yes, for next week, total for all tutorial will be not online, but I'll inform you what will be the means of class lah. Just to mention that I'll be the whole week going for a conference. Okay, so lecture will be maintained but fully online. Okay, as this lah, as this session. But for the tutorial, I'll mention or I'll inform you through the Google Classroom later on. Okay. When will be the test? Let me check the test. According to our teaching plan, the test will be on week 7. Okay, so next week is week 6. Okay, so we have quiz. If I can share this, where should I go? Stop presenting and show those entire screen. Okay, based on our teaching plan. Okay, so basically this currently is week 5. Okay, so we have a lecture. Okay, and then week 6 next week we have the quiz. Okay, where basically last time we have 1 to 3, right, for quiz 1. So quiz 2 will cover 4 and 5 lah. Okay, so 4 and 5. And then physical and detailing lah. So this part. Okay. And then for test will be week 7. Okay, so this one I'll quickly, if I get the actual date, Okay, I'll inform to you. Basically, what we plan is that we have everyone sit on the same time. Okay, not sure when we want to have it yet. Okay, but the test will be everyone, the whole class from other lecturers also will have the same time for the test. Okay, so and it will cover chapter 1 until 6. So that is what I can say just now. Say it right now lah. Okay, is an online test, right? Yes, for the test is online, but it will be subjective lah, not objective. The quiz will be objective. Yeah, the quiz will be online, MCQ. Yeah, uh, test is not MCQ. Test can have subjective question. It's a subjective question. All right. If that's okay. Anything else before I let you go? Okay. So I hope that you already have this information based on test is in Google Form. Yes, test that one will inform you later. But basically, TTLC no class, sir, from 3 to 5. We have an online class 3 to 5 for TTL6. Right. So if there's no further question, so I will say that this will be the end of for our today's session. Okay, and we resume next week. Okay, so perhaps next week I'll be lecture from KL Convec. Okay, so because I'll be there for the whole week. Okay, and perhaps we have a background of KL60 next week. Okay. The quiz will be on which day, sir? During lecture, Bukhari. It will be during lecture, okay, which is on Friday. Just wait when I'll share you the quiz lah. Okay, so I will end this. Okay, and I hope that you guys have a very good weekend. And those who are perhaps contributing to the convocation. Okay, so be careful and have a nice day lah. Right. So thank you very much. Assalamualaikum, and I'll see you on the next session. Right. Bye.